Okay, so I think we're recording, we're good here. I'll start here. Stat 121. First and foremost, did you have a good break?
Yes.
Yes. But now it's over, and that's sad too. Okay, what was the answer to the bonus? Where was it? First page, first sentence. It's in there. What? Are you serious? It's just a little experiment that I like to do. It is just a bonus, so I give part marks for guesses, whatever. It's just 3 marks, but it will always be in there somewhere. You will be able to find it. People spend way too much time looking for it sometimes. And I even had someone, because I usually say it's harder than you think, right? You know it's somewhere in there, you have to find it, and it's harder than you think. And then someone was all cocky and it's harder than you think, underlined it, but then they couldn't find it on the next test. So anyways, so they had to eat their own words, but made me happy. Yeah, so, but I do think it's pretty funny because people storm out of here. How am I supposed to know about manatees? So it's right there. But like I said, part marks for whatever. Chuckles are usually worth full marks, so keep that in mind. No pressure. What's gonna make her laugh though? She never laughs. All right. How did reading and understanding chapter 6 go? Well, we had probability assignments due last night. What do you think we were doing? I know. Hopefully you at least read it. So when we go through it today, it'll kind of fill in the cracks. So these tests are yours to keep. I will say, so I understand that it was long. It wasn't actually long, so I'm a little bit confused about that. So for next test, you really got to keep your pace up, right? And so especially for the final, because the final, I would say, is long. So you really gotta go. Okay. So we did cut some of that kind of by putting it on the lab exam, right? To have that kind of extra 50 minutes to do part of it. But I would still say it's pretty long. So you really got to work on your pace. Go. Yeah. No, there's been drafts floating around, and so I think once those are finalized, they will post those. They are out. They posted them. Ballsy. Okay. So then I actually don't know. I think maybe the 21st, something like that. Yeah. Seeing some nods. Cool. 21st. I did not know they were posted. Usually the campus is like buzzing. It's like, final exam schedule's out. You guys are keeping it under wraps. Okay, so like I said, these tests are yours to keep. Use them. Learn from them. I'll post the solutions. Yeah, well, don't burn them until you're done the course. Well, actually, until you know you passed the course. That would be important. So, all right, burn. On the plus side, we're leaving probability behind for a little bit. So that big monster is gonna go back in its closet. You won't have to think about it for a little bit. We're gonna say probability a lot, but not in the sense that we've been dealing with it so far, you know, pulling cards, pulling socks out of a drawer. What was that? If you think about it, the sock one on your assignment is exactly like the tree diagram that we did on the test, right? And so it's just that I had computed those probabilities for you, right? And so, but it's the same idea. So you have a bag of gift cards. First guest pulls a gift card. You pull one sock, right? Now there's fewer gift cards to choose from. The next guest pulls theirs, right? Pulling your second sock. Right? I'm assuming you all know what I am talking about because you were doing the assignments. But anyways, right? So exact same, and you can kind of convince yourself of that, except I made it, I'd say, quite a bit easier, of course, on the test. Any questions? No? No one's gonna ask me, what was the average? The one time that I'm ready for it?
What was the average?
Hey, really good question. 64 and a half, I think. So I'd say it was not a great test, but like I said, you really got to keep your pace up. Okay. Oh, and I know I'm blabbing, but I haven't seen you guys in so long. As long as you feel like you're able to do better on the final, don't worry about this test, right? We're just going to keep moving forward. And so if you do better on the final than on this test or even test 2, right, what I'll do is I'll just pretend you didn't show up, shift the weight to that final. So as long as you're improving and you're doing better and you do better on the final, you're good. Yeah.
Do you have to improve by a certain percentage?
No, I just blanket, push it all over. Yeah. So some people say you have to improve by, 10%, 20%, whatever. No, I'm just going for it. As long as you can do better on the final, because these questions are gonna come up on the final exam too, right? So if you can show me that you've worked on it and you know how to do those, then let's do it. Let's pretend that no one was here, shift all those weights over. Okay? So, like I said, keep the tests, learn from them, work on them. I'll post the solutions. All right. If we're talking about the average, should we know the distribution? I actually didn't look at the distribution of the grades. I'm assuming they're approximately normal. Because you read chapter 6, yeah?
Transition.
Yeah. Oh, the crickets. Okay. Tough crowd. All right. So, chapter 6 starts off and we talk about the normal distribution. Okay, and so the normal distribution is going to come back to haunt us for the rest of the term, and we're going to need it, we're going to use it, and so we need to have this kind of basic understanding of how it works. So let's see here. Chapter 6. Just realized I haven't written for like a week. Ugh. It can't be worse than after summer, right? Distributions. Of random variables. Wow. 6.1 is the normal distribution. So you read about the normal distribution, then you'll know that in the later sections of chapter 6, right, we also talk about the binomial distribution and the Poisson distribution. I want us to focus on the normal distribution for now. There will be a binomial question on the final, so we will work on that as well. But there's no Poisson questions, so we'll kind of sweep it under the rug a little bit. We'll work on it, but not really.
What is Poisson distribution called that?
Yeah, I think, I'm assuming it's like the guy that figured it out. It's always a guy, I don't know. I'm assuming it's a name thing, but I should probably look that up. Maybe they were counting fish, because it's a counting distribution, right? If you know the rate that some things appear at, then you know the distribution that these counts are going to come up at. So wouldn't it be funny if it was for counting fish? And I think that would be a really good question that I should make up later. But I should probably know where it came from. I'm assuming the guy who came up with it. So as we already said, we touched on the normal distribution, right? When we talked about describing histograms, right? Describing distributions. Oh, it looks approximately normal. So we know the shape, right? But the normal distribution describes so many naturally occurring distributions. So heights, weights, even speeds, if you're talking about a certain scenario, right? And so a lot of things follow a normal distribution, and that's why it's a main player. And so the normal distribution, oh man. I wish I could just dictate. Describes many naturally occurring distributions. Oh man. Sorry, guys. So we already talked about, okay, well, if I have this histogram, that's a distribution, right? Then to fully describe it, we have to talk about the shape, the center, and the spread. Okay. And so we know to describe a distribution, we need to describe a distribution the shape, which now we're just gonna zero in on a normal distribution, right? We're not gonna talk about skewed distributions, although they have named distributions as well, but that's for a later stats course. So we're talking about the normal distribution, which we know is this bell-shaped symmetric distribution. And so we also have the center, which if we have a normal distribution, we know we have to use the mean as our center. So if we've got this normal distribution, wait, disappeared. What we do is we say, okay, well, here in the center, that's where our mean is. Right? So our normal distribution is centered on the mean, and we denote that by mu, right? The population mean. And then the third is the spread, which again, going back to the fact that we're only talking about normal distributions, is the standard deviation. Which there are ways that we could show it on our little distribution here, right? Just like we put the mean in the center, but usually what we do is we just write the standard deviation somewhere below it, because the standard deviation is the spread, right? So it's just telling us how big of a variation are we expecting here. And so usually we just say something kind of below that distribution, right? And I guess maybe what I should do is do the original, kind of fill it in like I have been doing. So we've got this normal distribution. Everyone's centered on the mean, the population mean, and then it's symmetric around both sides, of course. And why do we care about that? Well, because here, if we've got everyone centered here, then it's very likely that you're going to be hanging around the mean. That's just how the mean works, right? And so as we move further and further away from the mean, right, notice how the area under the curve gets smaller and smaller and smaller. That's because the area under the curve here is a probability, right? It's the probability of these things happening. So it's the highest around the mean, right? Because that's where things are most likely to be happening, right? And then as we move further and further away from the mean, right, making it more and more extreme, right, the area under the curve gets smaller, and so the probability of those things happening gets smaller and smaller and smaller. So the area under the curve, whoops, is the probability. So like I said, we are going to say probability a lot, but it's going to be very different from what we have been doing. Oh, and what I wanted to kind of console you guys with was probability is always the hardest section of this entire course. So don't bog yourself down. Okay. I guess I can say that because we talk about probability in different forms throughout the course, but no, I mean that previous chapter that we just did, right? Chapter 5. So the area under the curve is the probability. Okay? And so what does that mean? Well, we know all the total probabilities have to add to 1, right? That's still going to be true. That's true for any probability. So for us, the total area now has to be 1. Right? And so this means that the total area under the curve, oh, come on. Under the curve must be 1. We're going to use that fact a lot, right? Kind of sneak peek, right? The Z table, it only gives you the area to the left of some value, right? But if we know the area to the left of that value and we know that the total area has to be 1, then we know the area to the right of that value as well, right? And so we'll get there, but because I know you've kind of seen it, right? I just want to tie it all together. Okay, so the total area under the curve must be 1, right? Another fact must be that, well, if it's centered on the mean, what area must be to the left of the mean? 50%. What area must be to the right of the mean? 50%, right? Because it cuts it in half. Okay. Since the area is symmetric about the mean, then if we've got the mean here, on this side we've got 0.5 and on this side we've got 0.5. So we can use that fact as well. So what we said was, okay, if we have a normal distribution, then what we need to know in order to summarize this distribution is, well, the shape and the center and the spread, right? So what we can do is we use some shorthand, instead of writing out blah, 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 follows a normal distribution with a mean of this and a standard deviation of this, there's just shorthand that we'll develop and use quite a bit. You know? And so to avoid saying whatever it is we're talking about follows a normal distribution, with a mean mu and standard deviation sigma, and just as an example, I'm just going to use x here. So to avoid saying x, and it can be, you know, the speed or the height of something or whatever you're talking about, right? So to avoid saying that x follows a normal distribution with a mean mu and a standard deviation sigma, right? We use the following shorthand. X, oops, follows, or follows a, so it's this tilde, kind of a squiggly line, follows a normal distribution, so a capital N, and then in brackets with a mean mu, comma, and standard deviation sigma, and then end bracket. Good luck. So, right, as long as we read this little guy, this tilde, as follows and then here, this n is a normal distribution. With a mean mu and a standard deviation sigma. So the only things that we would replace are the mu and the sigma, right? Depending on what the mean and the standard deviation is. The shape is always going to be n, and I do find that a lot of people want to replace that n with some number, but it's just saying, hey, this is the shape, here's the center, here's the spread. Right. So if I tell you that the heights of dogs follow a normal distribution oops. Now I have to make up numbers on the spot. They're not going to make sense, but well, probably. Distribution with a mean of 70 centimeters and a standard deviation of what, 15 centimeters? Give them nice big spread. Yeah. Follows a norm. Yeah, follows a normal distribution. I cheated on the distribution. With a mean of 70 centimeters and a standard deviation of 15 centimeters. Right? Oh yeah, it's follows a. Yeah. Because that's how we would say it, right? We would say something follows a normal distribution with a mean this and a standard deviation of this, right? And so that tilde is just taking the place of follows a. Yeah, it's this like, well, mine gets sloppy. It's supposed to be more like that, but usually I just crash it. I guess I could. Still looks the same. Anyways, it's a little tilde. So the shorthand here would be that the heights follows a normal distribution with a mean 70 and a standard deviation of 50. Nah. You'll want to keep the units in mind when you're interpreting it. But otherwise, no, I just ditch the units. Yeah, it's not something that we're going to have to worry about. It is something worth worrying about in real life, but not for these problems that we're going to do. Okay, so we've got a normal distribution with some mean and some standard deviation. And what do we want to do? Well, ideally, we want to be able to compare two values, right? Or I'm telling you that, right? We're going to compare two values. And what's nice about knowing that they follow a normal distribution is that we can actually standardize these values, so we can take values from two different distributions and compare them by standardizing them. Okay. And so I think of it as, you know, you've got a really tall dog, but you also know the distribution of the heights of the cats, right? Maybe you found a really tall cat and you want to know, well, which one is taller compared to their distribution, right? So what we do is we kind of boil it down to these standardized distributions, and that's where the Z scores come in. Okay? And so we can take values from two different distributions and boil them down to compare the standardized values. And so we can compare. So we can compare values from different, oops. Distributions by standardizing them. Different distributions by standardizing them. So as long as they both come from a normal distribution, then we can standardize them and pull them down onto these kind of smaller scale normal distributions. So we call these standardized values Z scores. We call these standardized values Z scores. So in the textbook, right, they use the ACT and the SATs, which are kind of high school, what kind of check your grades type of situations, right? I don't know. What do they call them? Competence? Yeah, it's like a, come on, guys. Yeah, it's like,
they're American.
yeah, it's like our provincials.
Yeah.
Yeah, anyways, let's say we had two different types of provincials that you had to write, and they're on different scales, right? I think one is maybe out of 200 and one's out of 25 or something weird like that, right? They're still gonna have a mean and a standard deviation, right? But you wanna compare, oh, I wrote the SATs and I got this score, right? Oh, I wrote the ACTs and I got this score. Well, who did better, right? So that's when we can standardize these and compare the Zed scores. And so let's talk about the Zed score. And so what we'll say is that if X, and now I'm going to use that notation, right? If X, so any observation X follows a normal distribution with a mean mu and a standard deviation sigma. So this is saying an observation X, whatever it is, comes from a normal distribution with a mean mu and a standard deviation sigma. I guess I should extend. So X is just an observation from this normal distribution. Let's say one of the scores that we want to look at. Then we can calculate, I'll put this on the next page, I think. Z equals X minus mu over sigma. Just kind of giving it to you straight here. Usually I take some time and I'll do it in reverse. I'll try it in reverse today. So here's our Z, right? And what's it doing, right? It's taking our observation, so the score that we got on the SATs, for example, and then I'm taking its distance from the overall mean score on the SATs, right? And then it's dividing it by the spread, right? And so the Z score is just saying, hey, X is this many standard deviations away from the mean, right? And so we just figure out how many standard deviations we are away from the mean to figure out the standardized values that we can compare, right? Because we can have different means and different standard deviations, right? But relative to the spread that we're expecting, right, we'll be able to capture that if we talk about how many standard deviations X is away from the mean. So the Z score tells us how many standard deviations sigma, right? Standard deviations is your sigma. An observation, and that observation is just X, is from the mean. Which is going to be our mu. Oh. Just as a quick example, right? If I said, well, how many standard deviations is an observation of 3.5, from the mean, or a mean, I guess, from the mean of, let's say, 4.2, if the standard deviation is 1. Well, let's do something let's make it 1.5, only because I didn't want to divide by 1.5. Let's see. We could talk about this on just the quick number line, right? If you just plop these down, so we've got 4.2 is here and 3.5 is here. And I want to know how many standard deviations, right? How many things of 1.5 can I fit in here? The first thing that you would do is you would figure out what the distance is between these 2 points, right? How many times can I fit 1.5 into this distance? Well, here, if we're talking about in terms of our x's and our mu's, right? This distance is going to be, well, the distance is going to be 3.5 minus 4.2. You could do 4.2 minus 3.5, but just as a rule, what we do is we do the x minus the mean, because that way we're going to be able to get negative values to indicate that, hey, these things are below the mean, and positive values to indicate that, hey, this is above the mean. All right, and so if that's what we're going for, then we're going to do x minus mu. And so this distance is going to be x minus mu. And I'll just make a note here. This will gives negative values if x is below mu. Right. So the distance is x minus mu, and so the distance in our case is 3.5 minus 4.2. I need these up, obviously, so let's see here. 3.5 minus 4.2 puts me at negative 0.7. And then how many times can I fit 1.5 in there? Not a lot, right? Not even once. So what does that tell me? It tells me that 3.5 is less than 1 standard deviation away, right? But we can pinpoint it because we know it's not at 4.2. 3.5 isn't at 4.2. So we can still get a decimal for how many standard deviations away it is from the mean. And so our z is going to be x minus mu, which we just kind of summarized as the distance. Oops. Divided by sigma. So in our case, we get z is 3.5 minus 4.2 over 1.5. I get negative 0.466 repeating. What does this mean? Well, we said that we're going to get negative values for z if it's below the mean, right? And so, and I'll summarize that in a little bit here, but so we're below the mean. So we're 0.46 repeating standard deviations below the mean. So what this means is that an observation of 3.5 is 0.466 repeating standard deviations below the mean. So some Zed Score facts. Right. A negative Zed score just tells you that, hey, this thing is below the mean. And a positive Zed score is, of course, that it's above the mean. So a negative Zed score, oops. A negative Zed score hate to use the word means in a different context, but I guess it works. So fancy. Yeah. A negative Z score means X is below the mean. And of course, a positive Z score means X is above the mean. As a blanket rule, we're going to round Z scores to 2 decimal places. Okay. And so we will always round Z scores to 2 decimal places properly, right? Of course, I'm not going to round illegally. Right? And the reason for that is because later, when we use our Z table, the Z table takes Z to 2 decimal places, right? So you always want to match your table because they're, believe it or not, George is not at home. No, no Seinfelders. Oh, okay. There's going to be more tables. There's going to be a T table, chi-squared table. Ugh. Right, so this is our first table that we're going to deal with. And so we're always going to match what the table is giving us. Right? And so the Z table, so we will always round Z scores to 2 decimal places to match the Z table. So if you're ever kind of stuck and you can't remember, this is not something that you need to memorize. It's just you need to look at the table and say, well, how many decimal places do I need? 2, great, that's what I'm rounding to. Right? But you have to round properly. Is it the end of the world if you don't? No, but you'll lose half a mark. So Z scores, right, we round to 2 decimal places. They're negative if we're below the mean. They're positive if we're above the mean. And of course, I'll put it on here just because it is a Z score fact. It tells us how many standard deviations we are away from the mean. Right. So Z scores are how many standard deviations, and I'll just do SDs. An observation X is from the mean. Also a Z score fact that we'll kind of parking lot for a little bit, but I do want to bring it up here, is the goal of stats is going to be to figure out, is this an extreme value or not, right? And we communicate that extremeness through probabilities, right? What's the probability of seeing something this large or this small, right? If we're out in the tails. As a rule, we say that any Z larger than 2, so -2 on the lower end or +2 on the upper end, right? Anything beyond 2, we would consider extreme, right? If we had to have a go-to kind of cutoff, anything beyond 2 in either end, right, would be considered extreme. So any Z score I'll say beyond plus minus 2 is usually considered extreme. Is usually considered extreme. And that's going to be good to have just a kind of an idea of, well, what's going to be considered extreme? We're going to develop that idea and kind of formalize it with hypothesis testing later on. But just as a rough guideline, would this be considered extreme? You calculated a Z score, you get a Z of 3.5. Would that be considered extreme? Yes, it would be, right? So you've got this extreme observation, right? And so what it looks like, oh, didn't like my line. There we go. I've got this normal distribution. And if I've got my Z scores down here, then at some point here at -2 and up here at +2, these values will be considered extreme. Right? So for any values that are beyond here or here, right, the positive side or the negative side, those would be considered extreme because you're so far out into the tails, right? Remembering that the area in the tail, right, gets smaller and smaller and smaller. And so the probability of those things happening, remember, is the area in the and in the tail gets smaller and smaller. So the probability of those things become smaller and thus more unlikely. What's another Z score fact? Z scores, if you've got an observation X, if you go back to the formula for Z, that is the mean. So we get an observation of 4.2. How far is that from 4.2? It's 0 standard deviations away, right? And so what's nice about the Z score or the Z distribution, right, still follows a normal distribution, but it's going to be centered on 0, and the standard deviation is going to become 1. Okay? And so Z distributions, the distribution of Z is normal, right? Because all we did was we took a normal distribution and we shrunk it down to now be centered on 0 with the standard deviation of 1. So it's normal with a mean of 0 and standard deviation of 1. So in shorthand, what can we say? Well, we know that Z follows a normal distribution with a mean 0 and a standard deviation of 1. And that's how we get those negative below, positive above, right? Because it's centered on 0. And the fact that it has a standard deviation of 1 gives it this kind of nice property, right, that we'll use even more later on. Okay, I know it's a lot. Did I miss anything on this page that I wanted to? No. Even though I haven't been following my notes at all. It's kind of blah. here's another fun thing. Here's another fun thing, hikes. So how I want you to think of it is in a problem, it'll say blah, blah, blah. So whatever it is we're talking about follows a normal distribution with a mean this and a standard deviation of this. And then it'll ask, what's the probability of this happening? Right? Whatever scenario. Probabilities. Come on, right? But we know that that's just the area under the curve, right? And so what we're really asking is, what's the area under the curve that corresponds to this situation? Okay. So, we will usually want to find probabilities. And I'm going to say associated with some observation. Associated with an observation. And did everyone get a copy of those chapter 6 examples? Are they still floating around? Did I print enough? There's a printout of chapter 6. Does anyone have them? It looks like this. Very basic, double-sided. You guys know? Does anyone have a pile somewhere? 2, 4, there. Just so we can read. Did it make its way through this part of the room? Okay. Cool. Yep. Got some extras here. You. Guess I printed it now. All right. So if you have a look, okay, let's just have a look at the types of problems that we're going to have to tackle and then work our way backwards, right? Because I think that's going to be the easier way to develop this. So I guess I have it here. If we look at the first problem, they're long and wordy and whatever, right? But a cereal manufacturer has a machine that fills the boxes. Fair enough. So the boxes are labeled 16 ounces, but if you buy a box of cereal and it says it has 16 ounces in it, we know that it's not going to be exactly 16 ounces, right? We know that there's variability in there, but it should be hanging around 16 ounces, right? If you picked up a box in the store and it was really light, right, you would say, hey, that's weird. It's supposed to be 16 ounces, right? You would have this extreme observation. So we already understand that something really light in comparison to the other boxes would be considered extreme, right? And so here, if the machine is set at exactly 16 ounces and the normal model applies, then of course, about half the boxes will be underweight and half the boxes will be overweight. You don't want them to be underweight because then people get mad that, hey, there wasn't enough in there, but also overweight, then you're selling more, you're giving away more product than what you're charging for, right? So pretty common problem to have. So if you set it at 16, that's not really that good. So what you do is you shift it up a little bit so that it overfills on average, right? But then it shifts that normal distribution, right, from 16 to 16.3. And so now everyone's kind of happier. And so blah, 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 blah. To prevent underweight boxes, the manufacturer has set the mean, or has to set the mean, a little higher than 16 ounces. Based on their experience with the machine, the company believes the amount of cereal in the boxes fit a normal distribution with a standard deviation of 0.2 ounces. And the manufacturer decides to set the machine to put an average of 16.3 ounces in each box. Hey, we were supposed to find probabilities. Probabilities, proportions, and sort of percentages, all those P words, they're all the same, right? So let's just make a note here that a probability is a proportion, which is roughly a percentage, right? All these 3 P's, when you see them, right, you're gonna say, oh, I need to find an area under the curve. These are all areas under the curve. Right. I say roughly percentage because remember when I said, well, if the mean splits it in half, then the area to the left is 0.5 and the area to the right is 0.5. I could have just as easily said 50%, 50%, right? Then the total area under the curve is 100%. So they're all the same. All of these are asking for areas under the curve. So what proportion of boxes will be underweight, right? If we think about how we would tackle this problem, well, what proportion? So I know I'm gonna have to find an area under the curve, which we haven't looked at the table yet. I know it's there and I'm pretty sure that's where I'm gonna find it, right? But first we have to decide, well, what does it look like to be underweight, right? Underweight would be anything under 16 ounces, right? So to solve these problems, we should draw the distribution, right, to help us kind of map out what we need to do. So we should draw the distribution to visualize the problem. So for part A there, well, we're told that these weights, they're gonna follow a normal distribution. So I already know the shape, of course. And we're also told that it's gonna be centered on 16.3. So busy out there. Yeah. So we've got 16.3 down the center, right? So it's centered on 16.3. We're also told that the standard deviation is 0.2. And like I said, there's no real spot to put it. So I just put it down below somewhere. Sigma is 0.2. Oh yeah. And then for this particular problem, right, I want to know what proportion of boxes are going to be underweight, right? And so we have to think, okay, well, what does it mean to be underweight? We're going to use that 16 benchmark, right? So here, somewhere, and it actually doesn't matter where you draw your line. It's just going to be to help you kind of see what's going on. right? So if you put 16 here, I know it's below 16.3. Like I said, it doesn't actually matter where it goes because it's just to visualize the situation. In fact, it might not be very helpful if you end up putting 16 here because you think it's really close, right? Because it's not very easy to look at. Right? So I just kind of put it somewhere in the middle-ish. So what you want to think about, right, is that this number line here this is where the weights go, right? So these are your observations, right, with the means and the measurements. And then what we want is we want to know what proportion of boxes would be underweight. And so the proportion that we're looking for, right, we said, well, a proportion or a percentage or a probability, they're all areas under the curve. And the ones that are underweight are all the ones that weigh less than 16. Right? So what we do is we draw this line here at 16 all the way up. And then we shade the area that we want. So this area is going to be the proportion of underweight boxes. Okay. All right. So how do we get there? All right. We know how to standardize things. So we've got a Z score. I've given you a Z table. I've kind of pushed my product on you. You need a Z table. You need a Z table, right? And so the reason we use these Z tables is because what we do is we feed it some Z score and it spits back the area under the curve to the left, which looks like exactly what I want. Right? What's nice about using Z scores is if we didn't have Z scores, we would have to have tables for every single scenario of means and standard deviations. It just gets out of hand, right? And very unnecessary. We can just standardize things. And so if we have a problem like this, usually I sketch it out with the original numbers. Sometimes I'll sketch it out with the Z score, like I'll show you. But what we'll do is we'll shrink this down to a Z score. Okay. So to find the area under the curve, we need to use the Z table, which means we have to standardize this score, right? We have to find the Z score. Which means we need to find the Z score. As long as you keep track of, okay, well, what's my mean and what's my standard deviation, then the other value, the one that you're interested in, that's going to be your X, right? And so the one that you want to find the area associated with, that's your X. And so we find that Z is X minus mu over sigma. In this case, our X is 16 minus 16.3 over 0.2. Divided by 0.2. I get a Z score of negative 1.5. I'm going to tack on the 0 because remember, we always do 2 decimal places. Right? never mind that there was only one here, we're still going to use 2 decimal places. What does that tell us? It tells us that 16 is 1.5 standard deviations below the mean of 16.3. All right, so now we have this Z score. So to find the area under the curve, actually, I think I already said that, so I'll start this differently here. To use the Z table, you take the first part of your Z score, right? So the whole number in the first decimal is going to be in the rows, the margin, the left-hand margin. So to use the Z table, I guess I should do it as steps. Find the whole number. Right, so -1 in our case. And the first decimal in the left-hand margin. What you'll notice, right, is that there's a negative side and a positive side to the Z table. So you'll want to make sure you're on the right side, right? So Z, and I've got the table here actually. So here, right, we've got our whole number and the first decimal on the left-hand side, and it starts on the negative, and then you flip and you've got the positives on the other side of the page, right? And then what we do is we match the second decimal with the columns up top. They're going to meet at some table entry. We call this your table entries, just to match what the little description is there, just so you can rely on that in the test, right? We think about it as a table entry. The table entries are the probabilities. Okay. And so what we do, right, is we go here and we find Z equal to -1.5. Let's see if I can, there. My second decimal is just 0. So what I'm going to do is I'm just going to meet these, right? Find the intersection of these two, and that's going to be this guy here. 0.0. Well, you've got it in front of you, so 0.0668 is what you should be looking at. Right? All right, let me summarize that. Find the second decimal in the columns, or it's just one column, I guess. In the column of the table. I guess you're spanning the columns, flip-flopping. In the columns of the table. So you feed it sub Z score, and then you go and you find the table entry. The table entry, the intersection of these two values gives us the table entry. And what I'll do is I'll steal it from here, just because I want you to know that it's on there in a test situation, right? It's up here at the top and people always ignore it, but it's actually meant to really help you out. So as long as you remember that the things in the body of the table, we call those the table entries, right? And it says, I'm just reading it, the table entry for Z is the area under the standard normal curve to the left of Z, right? So the table entry is just the area under the curve. To the left of Z, whatever Z you fed it. So if we needed the area to the right, that's when we leverage the fact that the total area is 1, and I can just do 1 minus the area to the left, and that's the area to the right. So in our case, right, for Z equal to negative 1.5, the area that we wanted was just the area to the left. So the table entry is the one that we want. So if we summarize this, and like I said, sometimes I do the Z curve, sometimes I do, just depends on my mood, but they do the same thing, right? So now my Z scores follow a normal distribution centered on 0. Translating that original curve that I drew to the Z score curve, now I'm here at negative 1.50. But all I did was I boiled it down to the standardized, and it's called the standard normal curve, right? And that's what they're calling it. But a Z of negative 1.5, this area was 0.0668 from the table. Do I do it now? The area to the left of Z equal to negative 1.50 is 0.668. What does that mean in terms of the proportion of underweight boxes? Means that 0.66 or 0.0668, 0.66 would be really bad. 0.0668 is the proportion of boxes that are underweight. And you can convert that to a percentage if you wanted to, but I encourage you to start kind of working in decimals. Sometimes it makes more sense to talk about percentages, especially if I've asked you for a percentage, but I would just leave it as the decimal. And so therefore, 0.0668 is the proportion of boxes that are underweight. The probability of finding a box that's underweight is 0.0668. Nice. So you've got those problems. I know I'm out of time here pretty well. You've got those problems. We're going to keep working through them next day. But I do encourage you to kind of look through them, try them on your own and see what happens. If you didn't get your test back yet, you can come grab it. See you on Wednesday.